Okay, so I want to talk about something with functions relating to the test. So everything's graded for that test. Sorry for the delay. You'll get back your exam in the next recitation, whether that's tomorrow or Tuesday, and you'll go over the free response, and we'll go over the multiple choice on Friday in lecture. The most commonly missed items, and then free response and recitation, and then you'll give those back, and then you can come into the office, my office, as often as you like, for as long as you like, and we'll get your test out and answer all your questions. Look that over, come in multiple times. That's all good. So, but I do want to talk about something I noticed. So, functions, right? We're living in the land of functions. Functions are super important. So let's talk about something. A function definition. What's a function definition? That's where we're going to define a function. We're going to define a function. So that looks like something like this. P of x equals square root of e to the x minus x to the 4.1. Okay? This is a function definition, okay? Function definition has, what is that called right there? Remember what that's called? We worked hard on it at the beginning of the semester, and we've been working hard on it ever since. There's a name for that. Function notation. Function notation always represents what? What does function notation always represent? The value of the dependent variable. We can use function notation to represent values of the dependent variable of a function. In a function definition, which value of the dependent variable does it represent? In the definition, if it's p of x or f of x, which value does it represent? It's kind of a trick question. All of them. All of them. Why? Because x is, what's x? The independent variable represents all possible values in the domain. So when you say p of x in the function definition, you're talking about all possible values of the dependent variable. And over here, this is called the rule. This is how you get them. How do you get every value of the dependent variable? According to the rule. Okay, so then we can say p of 2. And what is p of 2? It's a value of the dependent variable when independent is 2. You can just write this. It has meaning. Just what I wrote there has perfect meaning. It doesn't need anything else. It doesn't need you to compute anything. It means the value of this function p, or the dependent variable, when the independent is 2. And so we can use that. And we know, like if we plug that into GC, you put that in GC, and what does it do if p is defined well? It spits out the value. It tells you, oh, hey, I know what that is. And it tells you what it's equal to, right? Okay? So we could write, but then we could also write, what is it equal to? What is p of 2 equal to? We know what it equals because we have the function definition. What does it equal? Square root of e squared minus 2 to the 4.1. But you don't have to write that. But it does tell us then what that value is, what p of 2 is. But just p of 2 by itself is perfectly content to be by itself and have legitimate meaning. Okay, so here's what many, at least half of you did on the exam. You wrote something like this. G of x equals the integral from 0 to 2, say r g of t dt. Scores of you did this. So I want you to tell the person next to you, what's wrong with this? This is showing me that you don't quite understand function definitions, function notation. You don't quite get it because you're writing g of x equals that. Tell the person next to you, what's wrong with that? Extra? Okay, what's wrong with that? Volunteer. Yeah.
It's a function value.
What is a function value?
The integral from 0 to 2.
This is what? A function value, a particular function value? Like a, yeah, this is a particular function value. What, when x equals 2? So you could write, what is this really equal to? No, not g of x. Not g of x. You all did it. Not all of you. Lots of you did it. It's equal to g of 2. What is g of x equal to?
All of the values.
Right, so you could write integral from 0 to x. So it's kind of like, I don't know, I'd have to interview you all. But it's kind of like, you think whenever there's something to do with a function that you're writing down, you always just slap a g of x in front of it. And you're not really thinking about what that means. That has meaning. It's not just, here comes a function, or here comes something to do with a function, so I need this something of x, g of x, f of x. No, that has particular meaning. So we use it in the function definition, and it means every dependent variable for every independent value of the independent variable x. And so we use that when we set up a function definition. But if you're writing a particular value of the function, you don't do that. So that doesn't make sense. Is it better? Lots of you did that. Okay. So this has meaning, right? This has really important meaning. It's not just a label or here comes functions or I don't know. So I'd have to interview you to find out where that's coming from. Okay, very good. So we'll go over the most commonly missed multiple choice items on Friday, and then you'll go over the free response on in your next recitation. Any questions? Okay, here we go. So we're hard at work, right? Okay, what is work? Let's review. Work is force applied over a distance, some of you are saying. And the general formula, most basic way to calculate is work equals F. Okay? But just before we get to anything, just in like real simple, if I push this table with a constant force for 8 meters, the work, how do I calculate the work? Force times distance, right? Force times distance. But then we know force can vary. Your distance can be curvy. It can not be straightforward. That's when things are complicated, but we worked on that last time. And when that's true, we have the net accumulation of work function, or accomplished work. Accomplished work is what? So if I say so here, do I want W of X or W of a number? I'm going to define the general form of the work function, meaning all values of accomplished work for any value of X. And what would that be? Write it down. So you can write it down to do. retain that from last time. The x equals. And this is not even just not from last time, but from the whole semester, right? This is the same pattern. Every time we want the accumulation function, we know exactly how to write down its general form. So what is it? The work starting at A until X is? Hopefully you wrote this, right? This is the same thing, no matter what quantity we're dealing with. Volume, area, work. What else have we done? Surface area, arc length, right? If we're accumulating, then we can express it as the sum of little changes of that quantity. Okay? It's not the accumulation of the rate. That's a lot. That's something I often hear students say. We're not accumulating the rate. What are we accumulating? Little bits of whatever quantity you've got, right? So this is dW, right? How do we each little bit of work then we use the rate to calculate rate times change in, right? Y equals m dx, right? So that's the m dx. So we're accumulating little bits of our quantity to form the quantity function. We use the rate to get every little bit of the quantity. Okay? And what did we say the last time? We figured out that the rate of change of work is? Just the rate of change. Remember what we said? If a little bit of work is the rate times a little change in distance, then that rate must be? Because work is force times distance. Remember what we said? What's that? Nope. So look, work is force times distance. This is work right here. And it's the rate times a little change in distance. Therefore, the rate must be force, right? Force. Force times distance. Rate of change of work is force. Because whatever our current force is times a little change in distance gives us the little bit of work for that little change in distance. Okay, so for the pushy ant, we had this. So here's our rate function. So what is that rate function? What quantity is that? Force, right? But this was for the ant was pushing with a constant force of 0.03, so why all this stuff? So what is this square root about? Right, we said rate of change of work is force, and the force that the ant was pushing with was constant at 0.03, then why is the force not constant here? Because the constant force that the ant was pushing with was in the direction of how he was walking. Okay? And what is this force? What's that? In the x direction, right? So we need this arc length multiplier here for arc length to like transform this from direction the ant is walking to in terms of x, right? So it's kind of like the 0.03 is in the direction of ds, Multiplying by the square root then allows us to like transform that into dx. So this is that constant force transformed into the x direction. So this now becomes force in the x direction. So that we can write the work as a function of its horizontal distance, not distance along the arc. Does that make sense? So we can say this, right? So if the rate of change of force, rate of change of work is force, then we could also write work this way. The accumulation from a to x, f of t dt. Now that has to be the force in the a force in the x direction, like we have here. Okay, so that's a little review. So we want to talk about weight next. Any question on this? Is kind of a review of last time. Any questions?
So that the force is 0.03 or 0.03 times the square root of r.
Depends what you mean. They're both force. This is the constant force that the ant is pushing with, and it's turning, right? He's on a curvy path.
But now it's up like that.
What's that?
But square root 1 plus f quantity square.
Right. This takes that 0.03 force and transforms it and gives us the force in the x direction. The equivalent x direction force that will give us the work as the ant goes on the curve. Does that answer it? It transfers the 0.03 from the ds to dx. Is it better? Okay, other questions? All right. So what is weight? What is weight? Weight is force, right? So weight is a specific kind of force. It's the force of gravity on an object. So the weight of an object is the force of gravity on it, or the force required to keep it from falling, or to raise it steadily. So weight is a type of force. Weight is a type of force. It's the force of gravity on an object, which is the same as the force to hold it still, keep it from falling. Or just lift it slowly, right? Lift it steadily. So what are the metric units for weight? Kilograms? Newtons, okay? It's like the way that we think about and use kilograms in everyday use makes it very confusing. Kilograms is not weight. Kilograms is what? Mass. It's the amount of stuff. It's not gravity's pull. It's not the force on it. The force on it then, due to gravity, is newtons. But we think about kilograms as weight all the time, right? So you just got to be really careful. So when we have our science and math hats on, not our like just living everyday life hat, we have to distinguish that weight is newtons. Kilograms is mass. It's not weight. All right, what are the English units for weight? Pounds, right? So pounds and newtons are like apples and apples. They're both force units, so they can measure weight of something. Kilograms is not. Kilograms is not like newtons or pounds. Kilograms is just amount of stuff, mass. Okay, so here's the relationship between mass and weight. We can use F equals mg. If m is the mass in kilograms, you multiply by g, acceleration of gravity, that gives you the weight of the object. So this is weight equals mass times the acceleration of gravity. And on Earth, gravity is 9.8. So this is weight force. And this is, oh, sorry. This is mass. So this F equals mg allows you to find something's on Earth, which is, this is where we live, and so this is most things that we consider. If you have the mass, then you multiply it by g to get the weight, or the force of gravity on it. So when you come to problems and you need force, right? Because they're doing work problems, we're going to need force. If they give you the mass, you're going to use mg. They give you kilograms. But if they give you pounds, are you going to have some equation like this? If they give you things in pounds? No, because you already have weight. That is weight force. That is force. So in metric problems, when they give you kilograms, you'll have this initial step to transfer or get the equivalent weight force. But in English unit problems, they're just going to give you pounds. So there's no mg to calculate. You already have force if things are in pounds. Does that make sense? That's a common question that comes up. Okay, so let's look at a problem here. So we have a winch. Where'd it go? So a winch lifts a platform. A winch is this like gear here. It's this thing that rotates. And it lifts the platform from the ground to the top of the building by a thick cable. The cable weighs 151.77 newtons per meter. Notice that it weighs a certain number of newtons every meter, right? So the platform structure weighs 2815 newtons. The winch must lift the floor 93 meters for people to step out onto the building's top. Define a function w whose w values w of h give the accumulated work at each height h above the ground as h varies from 0 to 93. Okay, so I want to encourage you on a real-world problem not to have the mindset of, okay, what equation do I need? And I'm going to figure out where those numbers go into the equation and get the answer. So this is a really common kind of train of thought or mindset among students. It's like there's going to be some equation, and I'm going to take the numbers, plug them into the equation, and that's going to give me an answer. Okay, so maybe that works sometimes, but it's a very narrow path that doesn't allow you. It's not about good problem solving, and so then when something changes, you might not be able to do the variation on the problem. Okay, so we want a kind of a holistic way of approaching problems that gives us the ability to solve lots of problems. Okay. And so that starts by, rather than searching for an equation and plugging the numbers in, let's start by defining or just identifying possible relevant quantities in the situation. So rather than have the mindset of trying to get an answer, let's have the mindset, at least initially, of to understand the problem. Let's really understand the problem and the quantities involved. And by quantities, I mean, so examples of quantities would be like the air temperature, the width of the platform. This is what I mean by quantity. The heart rate of the person on the platform, etc. So that's what I mean by quantities. So I'll start attendance, and you just, in this situation, just try to come up with what is a list of quantities that just might be. Maybe we'll cut the list down. Maybe we'll eliminate some that won't be helpful. But what's as many possible relevant quantities in this situation as you can come up with. Okay, so and talk those through in amongst yourselves. Okay, so let's just throw out the ones you kind of initially thought of, and then I'll write down the ones you think are the real ones we got to focus on in this problem. So just what do you initially think of that could have been a possible relevant quantity? Just shout them out. What's that? The weight of the man, okay? Gravity, acceleration of gravity.
The acceleration of the going up.
The acceleration of the movement. What else? What's that? Weight of the cable. Weight of the platform. Displacement of the platform. Height, like height of the platform? Yeah, right? Where you have a function, what? W of? Certainly height is going to be important, right? They're telling us that it's the independent variable. Okay, so let's write that one down for sure. We got that one. And so of those that you guys shouted out, what's another one that it's like, okay, for sure, this is going to be important? What's that? Okay, except that we don't know that. So I guess we can include that in the weight of the structure. So we'll use so we can call it WP, say. What else is going to be important? The weight of the platform, the height. Alan?
The distance of the cable, or how much this is left.
Okay, can we call it length?
Yeah.
Length of the cable. To the winch. We really should be including units on this. So what unit will we want on that? In meters. Weight of the platform in newtons. Height of the platform in meters. Okay? What else is going to be important? Acceleration of gravity. And that's in meters per second per second. Anything else? There's something else that's going to be important here that someone said. What's that? The weight of the cable, right? So W, we'll call that WC. That'll be in newtons. There's also a really, really important quantity that we have not listed yet. Accumulated work, right? Accumulated work. And that'll be W of H. W of H will be accumulated work. And that's going to be in Newton meters. Joules is the same as Newton meters. Okay, so now we kind of understand the situation. We've got labels. Are any of these letters that I've used here, are any of them like constant quantities versus variables? Which one? Or ones? Acceleration of gravity we know is 9.8. Anything else on that list that's like known? Weight of the platform. That's the 2815. Yeah, the weight of the cable is really not just newtons, but what? Newtons per meter. And we know that, 151.77. It's
each meter weighs that.
how much cable do we have, right?
Oh, yeah, I got you.
Okay, so ones, values, these we assign letters to everything. Letters that we know the values of, if you remember, if you had Calc 1 with us, we call those parameters. Their values, they can change from situation to situation, but in the given situation, they stay constant. So if I give you a new problem, the weight of the cable will be different, right? But in this problem, it stays constant. That's called a parameter. If the value of the quantity changes within the situation, for instance, what height of the platform, length of cable to the winch, accumulated work, those are what we call variables. So within the given situation, those quantities are varying, okay? So parameters versus variables. We use letters for both. Parameters stay constant in our situation, but might change in a different situation. And then variables change in the given situation. All right, so if we want to write accumulated work, so let's take a look here. So we want to just pause life at a typical point here. If we want accumulated work, so we could start by writing, so we've got all that written down. I'm going to, for space, I'm going to take that off. You've got that in your notes. So let's just start with accumulated work as a function of h. We know what that is in general, so let's just write it down and then see what we need to do it. So I'm going to write that down in general. What is that? Accumulated work as a function of h? Or I could, let's use our general form here. What? A comma h? We'll do one better than what they wanted us to do. Say the work starting from what height a to any given height h. And we all should be able to write this down if we're just, in general, writing the accomplished work would be integral from a to h of. So there's one of two things I could write here in general. I could write rate of change of work, or I know what that is. What is that? Force, right? So F sub T dt. And in this case, the force we're talking about is what? What specific type of force are we talking about? Weight force, right? In this case, it's the work to lift something, so that the force is weight, right? That force is, like we talked about, weight is the force to lift something or to hold it steady. Okay, so we need the force as a function of h. So our goal here, if we can write force as a function of h, then we got it. So what's the structure of this function going to be? What's the rule? What's the rule going to be for force as a function of h, right? So what are we asking? At this height of h meters, what's the current force on the winch, right? What's the current force on the winch when the platform is h meters above the ground? So just don't go for a final answer. Just talk about structure or generally what we need to get there. Go. Okay, so I think, are you talking about L? We said L. Okay, and he's defined L. What is L? We can say in terms of H, L is 93. The whole distance to the ground minus how the high it is would be the length of cable left, right? Does that make sense? That should make sense. The whole thing is 93. And so if you subtract whatever height you've traveled so far, what's left will be the length, and that's 93 minus h. Okay, good. So really the structure of this, the general structure is the total force on the winch is going to be what? The total force in general will be? How are we going to calculate that? Good. So it's going to be that's going to be weight of the cable plus weight of the platform. And so we got the length of the cable is 93 minus h. So what will the weight of the cable be? That's the length of cable that we have. Right, it's going to be L times that, or 151.77 times R 93 minus times L, which we know is 93 minus H. That's the weight of the cable. Plus the weight of the platform? 2815. And that stays constant, right? That was just a parameter. It's the weight of the... So I think we're ready to write the... So this is our weight function at a height of h. So that's our force. The weight is the force on the winch. And so we know accomplished work is the integral of force, because force is the rate. So we're ready to write it down. So you're ready to write down the function. Go. Alan, did you get it? Uh-huh. Yep. How do you do? Agree? Got it. Done. So now with that function, right, I can start at any height A, right? This is a parameter. A is a parameter, right? It's like fixed in the situation. We could start at any height A, and then we'd know what the work is to any other height H. We could put that in GC, and it could crank out answers for us using the function notation, right? Questions on this example? You good?
Yeah.
Okay. Any questions, comments? Okay. One last topic. Can just cover it quick. Not too bad. But just as you come to these real-world problems, I really encourage you, have your focus be, I really want to understand the problem. Look at it from all angles. Define all the relative quantities in the situation before jumping into just formula and answer mode, right? Okay, last chance, questions. Okay, so let's talk about springs. So springs are governed by Hooke's law. So Hooke's law says the force required to keep a spring displaced from rest is proportional to the displacement from rest. Okay, so by displacement from rest, we mean like unstretched length. Okay, so this is showing the spring being stretched by a weight, but it could be horizontal also. It doesn't have to be vertical. But X is not the length, the whole length of the spring. X is displacement from unstretched length. So how much longer are you making it by applying a force to it? That's what X is. So that's important. It's not the whole length of the spring when you're done. So for instance, this is not, for that last stretch there, not equal to X. What is X? X is from here. So from there down to there. That's X for this case. Okay? So can you write, so what is Hooke's law? The force required to keep the spring is displaced is proportional to the displacement. So can we write Hooke's law? Force equals what? If it's proportional to x, then we have?
Wouldn't there be like a spring constant?
Yep, a proportionality constant. So this says that what? It says force is proportional to displacement, right? Force is displaced. And so this, right, is the spring constant. It's a different proportionality depending on how loose or stiff the spring is, right? For a slinky, it's a super low value of K. It only takes a teeny bit of force to stretch it all along. But like a strut, a shock on a car wheel, has a super high value of K. It takes a lot of force to move that thing. Okay, so K is a measure of the spring's stiffness, like I said. And so what do we notice about here? If this is true, then what's also true? The change in force is also that same proportion to the change in displacement. So what really is K? What is K? Do you recognize what that is? Rate of change, right? It's rate of change. Delta dy equals K dx. So it's the rate of change of force with respect to displacement. So what's the accomplished work then? What would the accomplished work be, say, to stretch the spring x, a distance of x? What's the accomplished work? So the work for the spring to stretch it a length of x would be what? Just apply what we've learned so far. Accomplished work equals integral from 0 to x of the rate of change of work is force. And look, force for the spring is kx. Therefore, rate of change is k times t dt. Right? If that's the force to stretch it a distance of t, then you're stretching it all these different distances, and it's a matter of accomplished work to get it out to a certain distance. So you got to add up all the little bits of force over those distances because that force is increasing. So there's our rate of change of work force of the spring. So accomplished work is integral 0 to x kt dt. Now that's for a spring with a constant spring constant with a spring constant. There are also, in your homework, you're going to have a cobra spring. K changes. This isn't hard. You can do it. But K changes as you stretch it or compress it. K is actually changing, so it's not a constant anymore, but it's a different newtons per meters depending on the compression, and you have a homework problem like that.